First, you have to fit a linear model. In this case, we're going to talk about two important libraries for speeding up our process. In this case, it's tidyverse for data manipulation, as well as Caret for building better machine learning models. You can see, work on some data. In this case, I'm gonna unload it from here, you see, and you can see what we have here around, and you can check. You can see how many columns we have. We have years, salary. So the idea here is to run a linear model trying to predict the salary for a certain individual given the years working. Then here we're going to plot our data set with certain conditions. You can see any text, the color, certain aspects for the lines, and with the title. You can see here. This is the idea. This. Well, because we only have two variables, one is going to be the dependent variable and another response. Check that if I create a line, more or less it's going to be good, right? With certain errors as suspected, right? Let's see if what is the best line that we can find to fit this. Okay, take into consideration this part here. You can see it's important to notice that when you are creating or trying to find the best line, maybe this part doesn't have any problem. However, this one here a little bit. So take into consideration that. Then, now, because we're going to follow the different steps into building a machine learning model, let's create a test and training set. We're going to use, in this case, a function from the Caret library called create data partition that is going to give us 80% as marked there for training and the rest 20% for testing. Then we create the index here, the indices. As you can see here, create the indices, and following this, we take those indices to take the different observation from any tech, that is our data set. The same for test. Now we have two different sets, because you mark here, here, and here. Why do we want to do that? Because we want to measure the model performance, given the box code transformation and not. We will see that. Now, how to build a model in R? It's very simple. You just use the function lm, and here you tell what is the data. In this case, I'm not going to use the initial dataset in tech. No, I'm going to use a training. You can see here. And what is my explanatory variable? Years. And what is my response, my output? Salary. And don't forget the field here to use. And there you go. We just fit a model. Now, the summary. It's important here. Now, see here, how to read linear model output. Now, we have here to see if the model is significant. The p-value is smaller than 0.05, then ds, the r square, or the coefficient of determination is telling me 83%. What else? Here. Is the variable significant? Is year significant? Here, and you can see here the column for p-values. Yes, it's telling me that my variable is significant to explain the salary of the person. And these two values here are the coefficient. Then, if I want to recreate salary given years, I'm going to use that. How are we going to do that? Well, you just type what salary is going to be, following the explanation there, minus 681.1, because that's our intercept, as you can see, plus 9,087.3 multiply the years. And that's my linear model, simple regression model. Given certain years, I can find what is the salary. Okay? But is this model right? That's the question that comes to us. Is this model right? Well, it's important that in statistics we use certain assumptions for building a linear regression model. Which assumptions? Well, we are going to type here. I'm going to tell you. I'm going to read. Something is, we're going to abbreviate it using line. Line stands for linearity. That means that the relationship between variables has to be linear. What else? Independency. Independency of who? Independency of the observations. One observation doesn't have to disturb how you collect the other observation. What else? Normality. Normality of who? Normality of who? Of the residuals. What are the residuals? The residuals, remember, residuals are equal to the real value, the real y, we're going to say it, minus the observed or fitted y. That's what the model is going to tell us. What is, given certain years, what is the salary? Those are the fitted values. Okay, and what else? This is for residuals. What else? Well, now the E is for equality. Equality. Equality of what? Of the residuals. Then, we're going to check if the residuals are near zero. Why? Because we want to reduce the errors of fitted values with the real values. Let's see that with some plots. An easy way in R is just run plot. And you can see here, it's gonna, you can see here in the console, we have certain plots. The first one is what we call homoscedasticity or equality of variance. Check here that we have 0 around here because it does want to reduce the errors. The residuals are those errors. And then I want all these errors around this horizontal line. But check something important. This other curved line. What is that? Well, it's telling me that there is some pattern, and we don't want that. We want to avoid those patterns. They should be scattered all around without any visual pattern or obvious pattern. But here I can see it. There is some pattern. That's a problem. That means that there is no equality of variance because the errors here are different than the errors here. And we don't want that. So there's a problem. Homoscedasticity is a problem. So we are violating. There is a violation of the assumption. The other one is going to be normality. All the residuals have to be normal. Remember that. Normality of residuals. Check. Well, we can say that those dots all around this line, yeah, maybe it's acceptable. Then here, scale location, there's no any problem. Maybe there are some outliers, as mentioned here, that could affect the performance of our model or the goodness of fit of our model. Now, here, with that cook distance, it's important to notice if we have certain outliers, but there's no big deal as you can see because all these cloud of points are in no such different way. So we don't have problem in that aspect, but the equality of variance is a problem. Now let's check. Other way to bring this information, as you can see, you have salary years. Let's check this, and I'm going to create, or I'm going to plot my information, my training, versus what the coefficients are telling me. The coefficients, where are the coefficients of my model? Here, in intake. Outline is going to be a line that is going to recreate what those points should be. Let's check. As you can see here, that was sort of line that I created at the beginning when I was explaining you. And you can see here, as mentioned before, there is this tiny tail that could have make us to have problems. Because the other ones are just looking fine. You can see here we have 0, but this one maybe are the ones that are causing troubles. That for our goodness of fit in our model. Now we have to do something about it. Before doing that, let's calculate the model performance. That's gonna be a baseline for comparing if it's important for us to check the assumption of the model. Let's see here, we'll use the function predict, and this pipeline is due to tidy variance, remember, and this is our model, and we're going to try to find what are those predictions or the fitted values. But check that those fitted values are now for test, because I already saw what was the model's performance in the output. Remember here, just check here, this is the model performance for the training, but now I want to know for my testing. Important, this observation have been used in or building the model. Let's check here, and now I'm gonna compare. Let's check that R squared, as I mentioned before, is already calculated. The root, mean square error, it's important, those are the errors, right? The smaller the better. And let's check now here. There you go. Now we can compare it. What is telling us this? Well, R squared is similar to R squared test. That means that its model is not overfitted because they are more or less close. Here, the M squared error, look that have identical values too. So the problem is not about the model performance, it's about the assumptions. So we're going to compare with our new model.